Hello guys. Can you hear me? Okay. Okay guys, how's it going? Is everything fine? So, as I said previously and as title suggests, this video is going to be about solving dynamic programming problems. We're gonna solve problems from easy ones and go to solve very challenging DP problems. Hello. And in order to join this live stream right now, you don't need to have any specific knowledge about dynamic programming. We're going to move forward together and start from, as I said, start from easier problems and move on to hard problems and solve all of this together. This video can be helpful for you if you're going to participate or you're going to prepare yourself to participate in USACO, IOI, or ICPC, or any other competitions related to competitive programming. So, shall we start now? I also put a link to all the videos related to dynamic programming that I have in the descriptions below, so that if you want, you can watch any of those. I have made plenty of videos right now about dynamic programming that if you want, you can watch them as well. And it's gonna be helpful for you if you watch them. I also, so far, we had 3 topic streams on dynamic programming so far. And this is our problem solving session that we solve these problems from easy problems to experts to problems for expert people. So you can check the link of all the related videos to dynamic programming below, and I think we can now start. I have a doubt in DP problem. I have. Okay, so we can check it there afterwards. I mostly check Telegram more than Discord, but I try to check Discord as well for this one. Okay, sure. So, let's get started. Guys, first of all, this problem, this is the first thing that I need to discuss when I'm trying to solve problems on DP. And you know that I've already discussed it before. So what is this? Well, the first thing that, when we discuss dynamic programming, the first thing that we always need to discuss is this problem that I will go over it once again very fastly. This is the easiest problem in dynamic programming that we must always talk about it. Assume that we have a tape. This tape consists of n cells. And we want to color this tape into black and white. Okay, as I said, this is the starting problem and this is the easiest problem. And we are going to start from this point and go to challenging problems. So let's talk about this first. We have a tape with n cells. Now we want to color these cells. Each cell can turn into white or black. So we can make every cell either white or black, in a way that we don't want any 2 consecutive black cells. So our black cells cannot be consecutive. So if you consider each 2 consecutive cell, they should be either white or white black or black white. We cannot have 2 consecutive black cells. We cannot have black black. You have to say that how many ways. If our tape has n cells and you are given n and assume that n is up to 10 to the 5th, you have to say that how many ways do we have to color this tape. And you have to answer it modulo some mod. For example, modulo 10 to the power of 9 plus 7, since this number can be very large. So what can we do, guys, on this problem? Very nice idea. Yes, exactly. So this way, I mean, so the first idea that you guys are discussing is this: dp of I is equal to dp of I minus 1 plus dp of I minus 2. That's a very good idea. But why? Why is that? So, because I want to talk about it very fast, I will say that how it's gonna be. So, assume that we have I cells. Let's solve it for any I from 1 to n, instead of just solving for one value. Guys, wait a minute, I have to change something. So sorry about it. I'll be back in 5 seconds. Okay guys, sorry about that, something happened, I needed to fix it. So, okay, so we are going to use dynamic programming in order to solve this problem. And what does dynamic programming says? What does dynamic programming say? Dynamic programming says that when you have a problem, let's divide it into smaller sub-problems. Let's divide it into many smaller sub-problems and solve all of those sub-problems instead of just solving that one instance that you have. So we are going to solve many sub-problems instead of solving just that problem that we have. So we have some fixed n can be, for example, 7. For example, you are given 7 and you need to say that how many ways do we have when n is equal to 7. But instead of just solving it for n equal to 7, this is just an example. We are going to define so many sub-problems and solve all of those sub-problems instead of just solving that specific case that we have. And how do we solve these sub-problems? Well, the point is that, first we need to define these sub-problems. Define these sub-problems. For example, in here, I define my sub-problems, all the cases of n from 0 to 6. So, I consider all the cases where n is going to be equal to 0, 1, 2, 3, 4, 5, 6. And also at the end, I put 7 itself, the main instance of the problem. I consider all these sub-problems and I try to solve all of these sub-problems instead of trying to solve only the main problem that I have. And how it's gonna work? How can I solve it for all these sub-problems? I will define dp of I as the answer to the problem if our tape is 1 by I. Now, when I want to solve dp of I, there are two ways. Either my last cell is going to be white. If it is going to be white, when I'm calculating dp of I, if my last cell is going to be white, then I have I minus 1 cells left that I can color them as I want. Just in this part, no two adjacent cells must be both black. So it's gonna be dp of I minus 1. So you can see that now that why we define so many sub-problems and we try to solve all of them. Because as you can see, we are going to use these different sub-problems to solve our original problem. So many sub-problems are defined, and these sub-problems help each other to be calculated. That's the main power of DP. So this is one case. The other case is that this last cell is black. If the last cell is black, the point is the cell before that is gonna be white, and therefore we're gonna have now I minus 2 cells. When the last one is black, the one before that must be white, and I minus 2 cells will be remain. Why the one before that needs to be white? Because if it is black, then we have 2 consecutive black cells, which is a contradiction. So this one must be white, and now we have I minus 2 cells that they can be any way. I mean, in any way that I solve it for I minus 2, the problem is going to be solved. It's only important that in this part I don't have 2 adjacent black cells. So I need to just add dp of I minus 2 to it. And because these numbers can be very large, I need to just calculate this modulo mods. So is it clear? Please let me know if this is completely clear for you. So this is just the starting point. Now we're gonna solve the CF problems that we need to solve. I just wanted to go over DP, that what was DP and why we use DP with this really easy example. And as you can see, this definition is the definition of the Fibonacci sequence. I've talked about it before as well. This sequence, f of I equal to f of I minus 1 plus f of I minus 2, is also called Fibonacci sequence. So the answer to this problem also was the Fibonacci sequence. I mean, the answers for different n's, for some n, is going to be the nth term of Fibonacci. If it is completely clear, please use this emoji or say that in the chat. You can also put a plus in the chat. Mod is just something that we use because our answer can be very large and it cannot fit into integers or even long. Since our number can be very large, instead of printing the actual number, we need to just print it modulo some mod in order to show that we have solved the problem. I mean, we do not need to print the actual answer in this case, because the number can be very, very large. Is it clear? Do we mod every value of I? For each I, dp of I will be calculated modulo mod. So is it clear? Now we have 6 problems, 6 very beautiful problems that we're going to discuss from Codeforces on DP. So if you're ready, we can start talking about it. Shall we start? Nice. Okay, so let's start talking about DP problems from the first one. So the first problem that we want to solve is this one. I send it in the chat. I send the link in the chat. All the links will be in the descriptions below of the video as well. What's the max rating problem is 2300. The maximum rating problem that will be solved is 2300. Okay, let's talk about the problems. The first problem that we're going to discuss is this one, cut ribbon, that I sent in the chat. It says that Polycarpus has a ribbon, its length is n. He wants to cut the ribbon in a way that fulfills the following 2 conditions. After the cutting, each ribbon piece should have length A, B, or C, and the number of ribbon pieces should be maximum. So we have a ribbon, we want to cut it into pieces such that each piece has either length A or B or C, and we want the length of the number of ribbon pieces to be maximum. You have to say that what is the maximum number of ribbon pieces that we can have at the end. So each piece should be either A or B or C, and the number of pieces we want it to be maximum. For example, in the first one, the total length is 5, and A is 5, B is 3, C is 2. We have two cases. Either just keep it as one piece of 5 because A is 5 and that is okay. That's one case. But this way we have only one piece. But we can also cut it into two pieces of 3 and 2. This way we're going to have two pieces. So because we want to maximize the number of pieces, the answer is going to be 2. Okay, and it is guaranteed that at least one correct ribbon cutting exists for this problem. This problem also has, since these constraints are small, this problem also has a brute force solution, but we're going to solve it with DP. DP solution is going to be very easy as well. So let me first tell you that how we can solve this problem. So as we saw, N and A and B and C are going to be at most 4,000. Maybe we also talk about the brute force idea as well, very short. But what we're going to say, first we want to define so many subproblems. What do you think the subproblems can be in this one? How can I define subproblems in this problem? So the first question, the first task to do is to define subproblems. What can be my subproblems in this problem? Yeah, you have very good ideas. So these are very good ideas. Yes, we get here that actually, yes, that is what we want to get. At the end, our final answer is going to be this, but how can we get there? So yes, so kind of dp of I, exactly, dp of I maximum pieces we can get from a ribbon of length I. How can we start with the first piece or the first ribbon? We want to cut it in several pieces. We have a ribbon, we want to cut it into several pieces such that each piece is gonna have length A or B or C, such that at the end the number of pieces will be maximum. So yes, dp of I can be this. dp of I can mean this. The subproblem for I, instead of solving it only for n, let's solve it for every I where I is from 1 to n or from 0 to n. dp of I means that the maximum pieces, if the length of ribbon, the length of the ribbon is I. So actually what we can say in here is this. We can just, when we want to solve this problem for I, we can just say that what is the last piece? What is the length of the last ribbon piece? It's going to be either A or B or C. Assume that it is A. Then do you agree that if my last piece is going to be A, I'm going to go to dp of I minus A. Now I need to maximize the number of pieces that I can have from here, and now my length here is going to be I minus A. So it's going to be dp of I minus A plus 1. If the last piece has length B, for example, then the rest of the ribbon has length I minus B, and I have to add 1 to it. And if it has C, it's going to be dp of I minus C plus 1. So at the end, I need to take the maximum of all these three because I have all these three cases. So the first case is that my last piece is going to have length A. The second case is that my last piece is going to have length P, B, or C. So we have these three cases, and we have to consider the maximum of these three cases because I want to maximize the number of ribbons. I need to see that I know that in this case I'm going to have these many ribbon pieces. In this case I'm going to have these many, and in this case I'm going to have these many. So I will take the maximum possible one among them. So my answer, dp of I, is going to be maximum of dp of I minus A, dp of I minus B, and dp of I minus C plus 1. And my base case is that dp of 0 is gonna be 0, and dp of I for every I not equal to 0 is gonna be infinity at the minus infinity at the beginning. At the beginning it's gonna be minus infinity, and then it will change. Because at the beginning I say that this is my base case, so before doing anything, so far my answer when the length of the ribbon is 0 is gonna be 0. I mean, without any ribbon pieces, I mean, if my length is 0, I cannot have any ribbon pieces. So I'm gonna have 0 ribbon pieces if my total length is 0. So I can make 0, but my number of pieces is gonna be 0. But initially I set dp of I for I greater than 0 to inf, because it means that so far I don't have any solution for I. So when I don't have any solution for I so far, I set its dp to be minus inf so that I'm sure that it will not update anything. It's so low that it will never be used to update any of these things. I mean, any of these i's. So when it comes here, it will not be in the maximum and it will not update anything. Is it clear? I'm sure that for any I, if it is not possible to cut the ribbon of piece I into several pieces of A, B, and C, its answer is not going to be greater than 0 at the end. And at the end, I just need to see out dp of n. And since there exists at least one solution, it's going to be greater than 0 for sure. This is going to be my final answer. Guys, in case that any of these things doesn't look very intuitive for you and you're not completely understand it, I highly recommend you to watch the previous topic streams on dynamic programming as well. As I said, I will put the links of all those videos in the descriptions below. It can be really helpful if you see those previous topic streams on dynamic programming as well, because I cannot go into very detail of the basics today, because as I said, it's gonna be a problem solving session mostly. I started from the beginning, but if you see that something you need more intuition for something, you can always use those previous topic streams as well. So make sure to watch the previous ones as well if needed. So far, is this solution for this problem clear? Let me know that if it is not. If it is clear, please use this emoji and put a plus in the chat. If it is not, let me know in the chat and I will explain it again. It seems like the change making problem. I'm not sure, I haven't seen the change making problem, but if it is like this, we see and codes and want to maximize instead. Yes. You can also look at it like coins, like we want to create n coins and we can, I mean, total value of n and our coins worth A, B, and C, and we want to maximize the number of coins we have. Yes, exactly. That's gonna be the same. How to be sure the number of base cases I define is enough. Well, you just need to make sure that your base cases, in your base cases, you want to set all the values, or at least set the values of some of the things that you're sure that by setting them, all the values will be calculated. For example, in here, I have calculated everything in my base case. I said dp of 0 is 0 and dp of all the other i's are infinity. So I have set the value of everything initially in here. So in here, initially, I set the value of everything. So it's going to be enough. Everything, I know that for 0, its dp is going to be 0. Because if my total length is 0, I can do it without any ribbon. So my number of pieces is going to be 0. But for every other I, so far I don't have any solution. So I set it to be minus inf. Wait a minute. Okay. Is it clear? Yeah, you're welcome. Nice. So this was the first problem. I highly also encourage you to accept these problems. Try to implement them and accept all these problems that we're going to discuss today. I put the link of all these videos in the descriptions below as well, so that you can access them and solve them. Okay, so shall we move on to the next problem? So let me bring something for a second. I'll come back in a second. Okay guys, sorry, I just needed my charger, but it's weird that it's not charging still. Can you hear me now? I needed my charger, but it's weird that it's not charging still. Okay, nice, okay. So, okay, let's move on to the next problem then. So, the second problem. It is now getting more challenging. The second problem is boring day from Codeforces. Let me also send it in the chats. Boring day. It says that on another boring day, Igor got bored and decided to do something. But since he has no friends, he came up with a game to play. Igor has a deck of n cards. The card number I from the top has the number ace of I written on it. Igor wants to play a certain number of rounds until the cards run out. In each round, he takes a non-zero number of cards from the top of the deck and finishes the round. If the sum of the numbers on the cards collected during the round is between L and R inclusive, the round is won, otherwise it is lost. So Igor wants to win as many rounds as possible. You have to say that what is the maximum number of rounds that he can win. N is also up to 10 to the 5th, and AIs are up to 10 to the 9th. So Igor kind of has a deck of cards. These are from, for example, top to bottom. These are from top to bottom, so 17 is on top, 8 is at the bottom. And each time Igor can just pick a prefix of these cards, pick some cards from top, and remove them. If the sum of those values is between N and R, he gets this one additional score. Otherwise, he gets nothing from this round. Otherwise, he will not win this round. He wants to win as many rounds as possible. You have to say that how many rounds he can win in total. He can play as many rounds as he wants. He can just remove these cards in many rounds as he wants. At the end, he wants to maximize his score. So in the input, you are given N, L, R, and A1 to AN. For example, in this case, L is 3, R is 10. So in his first round, he can pick these two cards. Their sum is 3, so he will win the first round. Then he can pick this card, the next card. It is 11 more than 10, so he will not win this round. Then he can pick this 3. In the next round, it is greater than, the sum is gonna be 3, so he will win another round. And then in the last turn, pick this 7. And it is again between 3 and 10, and he will win another round. This way, he will win 3 rounds in total. If he does this. In the second case, L and R are from 1 to 5. Since all of the cards have values greater than 5, Igor cannot win anything, because each time he will pick at least one card out, and so that card enough is going to be more than 5, so he will not win any of those. So is the statement clear? Does the statement make sense? So yes, we get to that. Now we can think that what we can do on this problem. Greedy can be a good idea in total, but how? I mean, how we're gonna use greedy? Okay, very good ideas. Very good ideas. Let's start talking about it. Well, in this problem, I can say that I have this deck of cards. Guys, first, let's assume that, I mean, there are two cases in total. When I play a round, I either win it or I lose it. Okay? By playing a round, I will either win the round or I lose the round. The first fact that I say can be that whenever I lose a round, I can assume that I will only pick one card from the top. So in the rounds that I lose, I only pick one card from the top. Why I can assume that? Assume that, okay, I mean, I'm gonna lose anyway. So in this round, I'm gonna lose. So assume that what I've done is to pick these cards and I lost. I mean, assume that in an optimal answer, I will pick these cards and I've lost. Well, the point is that I could as well just pick all these cards individually in different rounds. I mean, the worst that could happen is to lose all of them, which is not worse. I mean, in this way, I have won nothing. I have removed all these cards without winning anything. If I just remove them one by one, in the worst case scenario, I again win nothing. So nothing gets worsened. It's gonna be at least as good as what it was. So the point is that if I'm gonna lose, I can assume that if I'm gonna lose, I can say that I will just pick one card from the top each round. So each round that I lose, I pick only one card from the top. Do you agree with this so far? Doesn't make sense for you. So I say that each round, I mean, I can play in a way that each round that I lose, I will just pick one card from top. If you agree with it, please again use this one or put a plus in the chat. If you're not, let me know to explain it again. So there exists an optimal answer such that in every round that I lose, I just pick one card from the top from the top of the deck. Do you agree? Do you all agree? Okay, nice. So in every round that I lose, I will just remove one card from top. That's gonna be very helpful when we want to update our DP. So we're making our own work easier this way. So we are making our own work easier by this assumption. Our DP can be solved in an easier way this way. When we are sure that our only case that we lose, the only thing that we do is to remove one card from top. And also, when I win a round, I want to say that I will pick I mean, if I'm gonna win a round, I can just pick as much as the first time that the sum of my cards is gonna be greater than or equal to L. So when I win, I just take as many cards as needed, or let's say I just take the minimum cards needed. I just take the minimum cards needed to have my sum of those cards greater than or equal to L. So when I win, I just take as many cards as needed such that my sum is gonna be greater than or equal to L. Maybe I can take more cards as well, but I say that this makes sense as well. Because if in optimal answer I do something else that I win, I know that this sum is gonna be between L and R. So if I consider the first time that my sum is going to be greater than or equal to L, its sum is going to be less than or equal to that. So it is still less than or equal to R. At the same time, I know that it is greater than or equal to L. So this also makes sense, and this is going to be also between L and R as well. So if there is another way to win, if I only pick the first cards that their sum is greater than or equal to L would work as well. And then those additional elements that I did not use, for example, if in optimal answer I use these ones, I remove these ones, I can just remove these additional elements individually, one by one. I mean, the worst case scenario, I will not win anything from them. So again, I will win one round by just removing these elements. So if in optimal answer I have removed some elements and I've won, I can instead consider the minimum number of cards needed such that my sum is going to be greater than or equal to L. Remove that. By doing that, I win one round. And just for the rest, remove them one by one. The point is that in the worst case scenario, by removing the rest one by one, in the worst case scenario, I don't win anything. So I get the same result. In that case, by removing these cards, I did win one round. In this case also I will win one round. Does it make sense? So if I'm gonna win, when I win, I just take the minimum cards needed such that my sum is gonna be greater than or equal to L. Again, please, if it makes sense, use this emoji or put a plus in the chat. So I'm finding the structure of the final answer. I'm using some facts to find the structure of the final answer. I'm saying that when I lose, I just pick one card. I mean, there exists an optimal answer that can lie in this structure. When I lose a round, I just pick one card. When I win a round, I pick the minimum number of rounds such that its sum is going to be greater than or equal to 1. So this is how it's going to work. Now I can define my DP. Now I'm ready. Now that I've made this structure, I'm ready to define my DP. And this structure helps me a lot to update my DP. So I can define some DP of I. What do you think DP of I can mean? What do you think is a good definition for DP of I? So the first thing that, as always in DP problems, the first thing that we need to do is to define DP. Define our DP. What our DP is going to mean. So, what does DP of I mean in this problem? How can we define it? Maximum number of games, maximum number of rounds you can win from 1i to n. Exactly, nice. So, we have some cards. I mean, we have this deck of cards. Let's use another color. We have this deck of cards. DP of I can mean that if I start from I and go to n, in these parts of the cards, what is the maximum number of rounds that I can win? If I only consider this part, what is the maximum number of rounds that I can win? Why this is going to be helpful? Because you see that as we go forward, each time we're removing some cards from the top. So you see that the remaining of the graph, the remaining of the game, what remains in the game is something after that, something from some I to the n. So if for every I, we know that if we start from I and go to n, to the last card that we have in our deck, if I know that what is going to be the answer for those cards, this is going to be very helpful for me to find the final answer. Okay, so the point is that because by removing some prefix, anyway, some suffix will be left. Always, each state of my game is some suffix left in here. So the point is that I want to maximize the number of rounds that I will win in that suffix. So I need to know that for each I in the suffix that starts from I and goes to n, what is the maximum number of rounds that we can win. So there are two cases. Either I'm going to lose the first round or I'm going to win the first round. So I need to consider both cases and find that what is the maximum number of rounds that I will win in both cases. I don't know which one is optimal. Maybe it's optimal if we lose the first round, but that helps us to win more rounds in the future. Or maybe it makes more sense for us to win the first round. So we have to consider both cases, either when we lose the first round and when we win the first round. We need to consider both of these cases and take maximum. What is the answer if you lose the first round? I mean, how can we find out the maximum number of rounds that we can win if we lose the first round? We want to maximize the number of wins, so if we fix the maybe it makes sense that in the first round we will lose, but in the next round we will win. I mean, for example, I will remove I, and then I take an interval such that their sum is between L and R, and I will win the next round. So I'm not going to just lose them one by one. I'm going to just remove them one by one and lose. I said that I have two actions to do. One action is to remove one element and lose. One action is to just consider the smallest number of elements such that their sum is going to be greater than or equal to L. And if it was also less than or equal to R, just take those ones and win. And if it is going to be greater than R, then there's no way to win with a prefix from there, because the first prefix that its sum is greater than or equal to L has sum greater than R. So there's no way that you can win in that case. So from dp of, sorry, I had to show it here. So we either remove one element or lose, or we consider the minimum number of elements such that their sum is greater than or equal to L. And if it was less than or equal to R, we consider that we take these ones and we will win. But if its sum was greater than R, there's no way that we can win our first round starting from here. So, where do we go if we lose the first round? If we lose, now we're talking if we lose the first round. dp of I plus 1 if we lose. Yes, nice, great. Or in order to simplify things, let's say that dp of I is gonna be the last I cards. Because it might be a bit weird for you if I say I plus 1. Let's say that dp of I means that what is the maximum number of wins if we consider the last I cards. So I is gonna be now the number of cards. So if we lose the last round, now what is gonna be, now how can we update dp of dp of I? It will be updated from dp of I minus 1, right? Because we said that if we're gonna lose, we just take out one element from top. So we just need to delete one element from top, and now I minus 1 cards are gonna be left. So now we need to see that in the last I minus 1 cards, how many wins can. So as I said, if we remove the last card and lose, there are I minus 1 cards left, and we need to see that how many wins we can have there. So if we lose the first one, it's going to be dp of I minus 1. Is it clear? If it's clear for you, please put use this emoji or put a plus. There. So if I'm going to lose the first round, I'm going to use dp of I minus 1. What if I'm going to win this round? What if what is the case that I will win the first round? What is going to be the answer that way? Yes, sure. I will explain it again. I'm saying that if I want to lose, there are two cases. When I want to solve the last I cards, there are two cases. Either in my first round, in my first action, I will lose a round, or in my first action, I will win a round. So if I'm going to lose a round, I know that in every round that I will lose, I will just pick one element, remove one element, we remove one card. So I'm going to go to dp of I minus 1. It's just dp of I minus 1 plus 0 because I've won no rounds here. I had a rounds. My score from it was 0. I get 0 from it. I do not win anything. And then I'm going to move on to dp of I minus 1. Because now I minus 1 cards are going to be left. And I need to maximize the number of wins that I'm going to have there. So if I'm going to lose the first round, I'm going to go to dp of I minus 1. What if I'm going to win the first round? Yes, we can either use lower bound or 2-pointer for the rest of it. So the point is that if I'm going to win, I need to find the first prefix. I need to find the minimum number of cards such that their sum is greater than or equal to that. So in order to do that, for example, I can do a 2-pointer. How does this 2-pointer work? When I'm iterating over these elements, I can use another pointer as well. And when this pointer moves forward, I can consider this other pointer, and as long as I can move this next pointer and still the sum of the elements in between is going to be greater than or equal to L, I'm going to update my sum and move this pointer forward. So if these are my elements, let's just write it like this. When I move forward and I add another, I will move my elements forward. This is the bottom of my deck, and this is the top of my deck. I'm starting from the bottom. Each time I'm just solving the problem if I consider the first I cards from the bottom, not from top. As I'm moving this forward, I can have another pointer that shows that what is the first point, the rightmost point, such that the sum in here is going to be greater than or equal to L. When I move this right pointer forward, it comes here. The point is that I can have a while. First, I add this value to sum, to my current sum, will be added by this new element. For example, if this is x, will be added by x. And I can say that while this current sum minus this last element was still greater than or equal to L, I will move this left pointer forward as well. So I will move it as much as needed. This way, using 2-pointer, I can easily find out what is the minimum size of an interval that ends here, such that its sum is going to be greater than or equal to L. And when I know that, I just need to check if this sum is also less than R. Assume that these are, for example, L elements. If this sum was also less than or equal to R, I can just update dp of I from dp of I minus L plus 1 as well. And do not forget that L also can be 1. If L is 1, it means that even if we remove one element from top, that is going to be between L and R. So it means that even by removing one element, we will win that round. So in that way, also we do not need to worry about considering this case of lose. We know that we will never update from here. Since we will win one round in here, even if by removing one element we will win, we don't need to worry that's why we also considered it in the case that we will lose the first round, because we will never update our answer from that. We will never update our answer from this dp of I minus 1, because then in here L is going to be 1 and we're going to update it from dp of I minus 1 plus 1. Therefore, if we know L, why I used L? L, we had L in here. Let's say D, sorry about that. Let's say D. So, if I use this D, if D is the minimum length of an interval such that its sum is greater than or equal to L and less than or equal to R, I will just update my dp from dp of I minus D plus R. Because I can remove these D elements and their sum is between L and R. This is the first place. D is the minimum number such that if I remove D cards, their sum is going to be greater than or equal to L. If that was also less than or equal to R, I can update my dp from dp of I minus D plus R. Does it make sense? As you said, we could also use lower bounds. That would also work. But you could also use this 2-pointer. And this way, this approach, your total time complexity is going to be n of n. If you would use lower bound, it would be n log n. Both work and are completely okay. Does it completely make sense as well? If you are okay with that, please again put a plus or use this emoji. Nice. The brute force solution of the first problem, yes. In the first problem, the point was that n and a and b and c were up to 4,000. And since they were up to 4,000, you could just fix that how many A's you're gonna have and how many B's you're gonna have. It's gonna be 4,000 by 4,000, so it's gonna be 4,000 squared. And then the number of C's will be uniquely determined. So you're gonna have one way for C. So you're gonna have 4,000 ways that for how many A's you're gonna have, 4,000 ways that how many B's you're gonna have. And if there is a way to fill the gap, fill the rest with C, there's only one way for that. So you can check if it is valid. If you can do it, fill the rest of it with C's, and if you can, there's only one way. And then you will just sum up these coefficients. We have x A's, y B's, and z C's, so it's going to be x plus y plus c. Okay, so let's get back to the this problem. There is a question that why did you start from the bottom? Well, the point is that, as I said, when we have these cards, when we removed several cards from the top, oh, thank you. And also, is this question clear? I made a mistake. I don't know why when I'm checking the chat, I forget to change the screen. So anyway, this was for problem 1. So we fixed that how many A's do we have, how many B's do we have, and how many C's do we have. And the point is that for C's we have only one way, and for this last problem, the point is that we do it from the bottom, since when we remove some elements from top, when we remove some elements from top, the point is that each time the remaining cards are some cards from the bottom. So each state of your problem, in each state of your problem, if you see that which cards are left, there are some cards from the bottom that are left. So each state of your problem is that, okay, these cards are left. What is the maximum answer that we can get from these cards? Okay, so in each, when you just keep removing some elements from the beginning, from top, in each state of your problem, you have some cards from the bottom that are left. So you can see that, you can say that what is the maximum number of rounds that we can win from those cards. Is it clear? Anas? Shall we move on to the next problem now, or do you have any other questions? If you have any other questions, let me know. Otherwise, we will move on to the next question. Okay, so shall we move on to the next one? No. It doesn't worth anything to know that what is the answer if some cards from top are remains. Because those are not valid states. So in any way, if you're gonna use recursive or if you're gonna use DP, because each of our states, some cards from the bottom are removed, and some cards from top are removed, and some cards from the bottom are remains. We need to see that what is the answer in this case. So dp of I means that the I cards from bottom are remained, and n minus I cards from top are removed. If you see it differently, like cards from the bottom are removed and only these cards from top are left, that doesn't make sense, since we need to do our DP from the bottom. Okay, so the whole point is that in each state, I cards from the bottom are remained and n minus I cards from top are removed. So you need to solve each of these cases. Nice. So let's look at the next problem chocolate bar. It says that you have a rectangular chocolate bar. Let me also send the link in the chat. Okay, as I said, this problem says that you have a rectangular chocolate bar consisting of n by m single squares. You want to eat exactly k squares, so you may need to break the chocolate bar. So you have a chocolate bar, it is like a grid of n by m. You want to eat exactly k squares out of these n m squares. In one move, you can break any single rectangular piece of chocolate into the rectangular pieces. You can break only by lines between the squares horizontally or vertically. The cost of breaking is equal to the square of the break length. For example, if you have a chocolate bar consisting of 2 by 3 unit squares, then you can break it horizontally and get 2 1 by 3 pieces. The cost of this is the length of the break to the power of 2. So the length of the break, when you have a 2 by 3 and you break it into 2 1 by 3s, the length of your break is 3. So the cost is going to be 3 to the power of 2. It's going to be 9. If you break it vertically in two ways and get two pieces, 2 by 1 and 2 by 2, the cost of this breaking is going to be 2 to the power of 2, because you have 2 by 3. If you break it vertically, the length of your break is going to be 2. So your cost is going to be 2 to the power of 2, it's going to be 4. For several given values n, m, and k, you need to find the minimum total cost of breaking. You can eat exactly k squares of chocolates if after all operations on breaking there is a set of rectangular pieces of chocolate with the given total size to k squares, with the total size equal to k squares. The remaining n, m minus k squares are not necessarily form a single rectangular piece. So basically what it says is that you have a chocolate bar, it has the rectangular form like this of size n by m. It is like a rectangle of n by m. Each time you can break it into pieces. So you can either break it like this or break it like this. Each time, initially you start from one piece, but as you go forward, you're gonna have several pieces. You can break each piece horizontally or vertically. And the point is that if you have a part that has size I by j, the cost of breaking this, if you break it horizontally, it's going to be j squared. If you break it vertically, it's going to be I squared. So it's going to be the length of the cut squared. At the end, you want to have a set of these chocolate rectangle pieces. The sum of them, you want the sum of them to be k, so that you only eat those parts. You want to eat k squares in total. So you want to break it such that at the end, a subset of them, a subset of those rectangles, have sum equal to k. You need to say that what is the minimum cost in order to do that. Is the statement clear? This is dp of I and j and k is going to be a very nice idea. We can talk about it. Do you have a sheet of dynamic programming problems? I have a sheet of problems of difficulty 2000 plus that I was solving before, and there's videos for them as well. Let me send it maybe in the chat. So I have 6 videos for problems with difficulty DP problems with difficulty at least 2000. I send you the sheets. This is exactly the sheet, and the point is that you can make a copy of it. You can come here and make a copy of it for yourself, and whenever you solve the video, you can just write solve in front of it, and every number will be updated. And if you click on these videos, you can see those videos as well. So all the videos are here. I'll send you the link. If you want, you can watch it. So maybe it was better if I just copied this part of the link. So this is a sheet we have. I also put the link of all the videos and live streams related to competitive programming, related to dynamic programming in the descriptions below. And yes, there is a Discord and there is a Telegram channel. There's a Discord server and there's a Telegram channel that we have that you can join. Feel free to join any of those. They are exactly for you to discuss your doubts. They are for further discussions. I put the link of both of them. This is the link of the Telegram channel, and this is the link of the Discord server. You can join any of them if you want, and you can have further discussion there. So let's get back to the problem now. Okay, sure, Peter. Thank you very much. Thank you very much, Peter. That really means a lot. Thank you. Okay. So let's get back to the problem. As we were talking, this is gonna be our final answer. That final cost that we have, we want to minimize that, and we want to see that what is that minimum possible cost that we can add at the end. Is the statement clear? If it is clear, please again use this emoji or put a plus in the chat. So we want to eat exactly k squared. We want to break the chocolate into several pieces such that a subset of them will have size k in total. One of the ideas that you said that was very interesting and could be helpful is this dp of I and j and k, that we can talk about it. So let's talk about this. We can, for example, have some dp of, we have n and m and k given. So if we define some dp of I and j and l, And do not forget that the constraints. The constraints are like this. We have n and m up to 30 and k up to 50. So k is at most 50, k is not more than 50, n and m are not more than 30, and obviously k is also up to n and m as well. And our t is up to like 500,000, up to 50,000. So it's up to like, for example, 5 times 10 to the 4th, or 10 to the 5th half, around that. So the point is that we do not need to care about the test cases. If we can solve the problem for every possible values of n, m, and k, and have them in our DP, for example, DP of I and j and l says that what is the answer if the size of the chocolate bar is I by j and we want to eat exactly l squares. If we know all of them, then each time we just seen n, m, k, and just right after that we see out DP of n, m, k. So if we know all the DPs, we just say that, for example, for each of those test cases, we have some while, we say while t minus minus, let's just define nmk, sin nmk, and right after that, see out dp of n and m and k. So if we define all these dp's, then we're done. I mean, if we define all the dp's and calculate all of them, then each time we can just see n, m, k, and instantly see out dp of n and m and k. So now the question only is that before this, well, how to calculate the dp's of I and j and l for every possible values. I and j are gonna be up to 30, and l is gonna be up to 50, and l is also gonna be at most I times j as well. So now my question is that if I have an I by j chocolate grids and I want to eat exactly L chocolates, L squares, what is the maximum, what is the minimum cost needed to eat exactly L squares? So the point is that when you have this I by j, there are some base cases. Can you say that what those base cases are? Initially, what are the best cases that we can define? In this problem, the best cases can be a bit more tricky. So what can be our base cases? What are the DPs that you can initially set them? If k is equal to 0, yes, that is a good case. And if k is equal to ij, exactly. So if L, since here I have I and j and L, I use L. If L is 0 or I times j, dp of I and j and L is going to be 0. Because in these two cases, we do not need to have any breaks at all. Initially, we can just eat it all or do not eat it all. So we do not need any breaks if L is equal to I times j or L is equal to 0. In these two cases, we do not need any break. However, if L is greater than 0 and less than I times j, we're going to need breaks. And if L is greater than I times j, there are no answers at all. So we can initially set dp of I and j and L equal to 0, and we can set all the other dp's equal to infinity initially, which means that so far we don't have any answer for them. And then as we go forward, each time when we want to calculate it for the answer for some L is from 1 to I times j, so L is greater than 1 and less than I times j. I have to set my first cut. Where my first cut is this. My cuts can be horizontal or can be vertical. So I can fix that how I want my cuts. How many ways do I have for my cuts? How many horizontal cuts I might have? How many possible horizontal cuts I have? I know that I have I rows, so how many horizontal cuts I might have? How many possible horizontal cuts I have? I mean, how many choices? how many choices. So for the first cut, I want to see that how many choices I have for the first cut. How many choices do I have for the first cut? N minus 1, yeah, or I minus 1. Since I have I rows, as I said, yes. So for the first horizontal cut, if I'm gonna have a horizontal cut, I'm gonna have I minus 1 choices. So for horizontal, I'm gonna have I minus 1 choices. For vertical, I'm gonna have j minus 1 choices for my first cut. And then I can say that, okay, let's say I made these cuts. I can fix that how many of these squares I want to eat from these parts, how many I want to eat from these parts. So I can fix, for example, I have some L, I can fix some L1 and L2 such that L2 is gonna be L minus L1. The sum of L1 and L2 is gonna be L. I can fix L1 and L2 that says that how many chocolates I'm gonna eat, how many squares I'm gonna eat from this part, and how many squares I'm gonna eat from the other part. So as soon as these are I1 and I2, I split it into two parts like I1 and I2 such that I2 is equal to I minus I1 and chocolates are L1 and L2. The point is that dp of I and j and L, I can say that it will be mean equal to, this is just an operator for explanation, this is not a real C++ operator. It's going to be equal to dp of I1 and j and L1 plus dp of I2 or I minus I1 and j and L2, L minus L1. And the point is that since I had I minus 1 cases for horizontal rows, I know that my total dp, I mean my dp has n squared k cases. So the size of my dp is n squared k. And I know that the number of choices for I1 is at most n. When it is at most I minus 1, it is of order of n. And also the number of ways to split L into two parts is going to be k as well. So my update is going to be n by k. I also do the same thing for vertical cuts as well. The point is that for vertical cuts, I have at most m choices as well. M is also like n, the constraint of m and n are the same. So for that one is also be n by k. So my total time complexity this way is going to be n squared k times nk. So it's going to be n cube k squared. And with the limits that I have, that n is up to 30 and k is up to 50, this is going to work. So I solved the problem with time complexity n cube k squared. Yes, at the end you're right. I have to also say that if I do this, the size of my cut is gonna be j, so I need to add j squared to this j squared to this dp as well. I need to add j times j at the ends to this dp. You're right. And if I'm making a vertical cut, I need to add I squared at the end. You're right. So, does this make sense? Please, again, if it makes sense, use this emoji or put a plus in the chat. Shall we move on to the next problem of DP? Okay. Well, thank you very much. So nice. Let's now move on to the next problem. Working out. Well, this problem says that let's read the statement. Let me also send you the link such that if you want you can read it as well. So this problem says that summer is coming, it's time for Laub and Laubina to work out as they both want to look hot at the beach. The gym where they go is a matrix A with n lines and m columns. Let's number A sub I sub j represent the calories burned by performing workouts at the cell of gym in the ith line and the jth column. Laub starts with workout located at line 1 and column 1. He needs to finish with workout A sub n sub m. After finishing workout A sub I sub j, he can go to 4 workouts A sub I plus 1 sub j or A sub I sub j plus 1. So A of I plus 1 and j or A of I and j plus 1. Similarly, Laubina starts from workout with workout A of n and 1, and she needs to finish with workout A of 1 and m. After finishing workout from cell A of ij, she can go to either A of I and j plus 1 or A of I minus 1 and j. There is one additional condition for the training. They have to meet in exactly one cell of gym. At that cell, none of them will work out. They will talk about fast exponentiation, and then both of them will move to the next workout. If a workout was done by either Laub or Laubina, it counts as total gain. Please plan a workout for Laub and Laubina such as total gain to be as big as possible. They can perform workouts at different speeds, so the number of cells they use to reach mid-cell may differ. So, what does this problem say? Let me say this problem in another word. So the point is that, in this problem, we just have a table, we have a grid, there are some numbers written on it. I want to choose two passes in this problem. One pass from the top left cell to bottom right cell, and one pass, so I want to choose a pass like this, and also choose a pass from the bottom left cell to the top right cell like this, such that these two passes only meet in one cell. They have only one intersection, these two passes, and I want the sum of the cells in these passes other than this green cell. This intersection does not count, but the rest of the cells that are in exactly one of these passes, I want the sum of their values to be maximized. So I have a table, I want to choose two passes from top left to bottom right and from bottom left to top right, such that the intersection is only one cell, and the sum of the cells other than that intersection cell is going to be maximized. And my conditions are that n and m are going to be up to 1,000. A of I and j is also up to 10 to the 5th. So this is going to be the whole statement. Is the statement clear? So I want to choose two passes, one from top left corner to bottom right corner, one from bottom left corner to the top right corner. The intersection must be 1. And at the end, I want the sum of all the cells other than the middle points to be maximized. Okay, let me know if there was any issues with this statement. So, how can I solve this problem? Well, in this problem, I'm going to use several DPs. This is an example of a problem we're going to use several DPs for that. In total, I'm going to have 4 DPs. Exactly, 4 DPs. Yeah. DP of 1 and I and j, DP1 I and j, DP2 I and j. I could also have this 1, 2, 3, 4 as another dimension, but I just prefer to, for now, write it like this. for explanation. But if you want, you can also use this 1, 2, 3, 4. I mean, have them as dimensions. So have a 3-dimensional DP such that the first dimension has 4 cases. What does this DP say? DP1 says that what is the maximum total sum of a path from the top left corner to this cell. And do not forget that this path can only go to the right and to the bottom, and this red path can only go rightward or upward. The blue path can only go rightward and downward. The red path can only go rightward and topward. So the point is that in here, dp1 of I and j means that if I start from the top left corner and I want to end up at cell I and j, what is the maximum cell sum that I can have? If I want to end up at I and j. And each time I can go only rightward or even rightward, either rightward or downward. dp2 of I and j is that what is the sum if I start from the top left, top right corner and go to I and j. And I can only go downward or leftward. dp3 says that what is the answer if I go from bottom left corner to this cell of I and j. dp4 means that what is the total sum if I go from the bottom right corner to this cell of I and j. So I have all these. Let's say this one is also updated like this. I have all these 4 dp's. And now, how can I calculate this dp? Well, for example, I tell you that how dp1 can be calculated, and the rest of them are going to be exactly the same. dp1 of I and j is going to be, yeah, exactly, Abdullah. Yeah, nice. Nice, Abdullah. So, dp1 of I and j is going to be like a of I and j. We definitely have a of I and j because we have a path to cell I and j. So a of I and j can be calculated plus maximum of, I mean, if I have a path from the top left corner to cell I and j, if I have a path like this, I know that the cell before I and j is going to be either I minus 1 and j or I and j minus 1. I have to, my previous one have to be one of these two. So I need to calculate the maximum of dp1 of I minus 1 and j and dp1 of I and j minus 1. So I need to see that what is the maximum of these two dp's. So dp1 of I and j can be calculated like this. Does it make sense? So this is how dp1 can be calculated, and the rest of the dp's can be calculated in the same way as well. And now when I want to see that what is the final answer, all I can do is this. I mean, it's just enough to do this at the end. When I want to see that what is going to be the final answer, I can fix the points and assume that this is going to be my intersection. And the point is that one thing that I can do, one thing that comes to people's mind first is to just sum up those 4 dp's for this cell. But that's not going to be correct, because that is, I mean, if you just sum up the 4 dp's for I and j, the point is that you know that I and j is going to be in intersection, but maybe you have more intersection cells. Maybe there are some other cells that are in these 2 passes as well, and that's going to be bad. So it's not going to work if you just add up dp of I and j for all of them. The point is that these 2 passes, this blue pass and this red pass, the point is that one of them should pass over this intersection cell horizontally, and the other one should pass over this cell vertically. So I can just fix that, how the blue path is going to pass over this cell and how the red path is going to pass over this cell. For example, either there are two cases. Either the blue path is going to use these two cells and the red path is going to use these two cells, or vice versa. The red path is going to use these two red cells and the blue path is going to use these two blue cells. It's one of these two cases. It's the only two cases that the intersection is only going to be in this cell. And this way I can just easily just sum up dp1 of this cell plus dp4 of this cell plus dp2 of this cell plus dp3 of this cell. And in this case I can add dp2 of this cell plus dp1 of this cell, plus dp4 of this cell plus dp3 of this cell plus dp2 of this cell. So each time I fix that intersection point, I fix that how the blue passes over this cell, how the red path will pass over this cell, and just add the corresponding dp's. And this way I can find the final answer. And the point is that if I do so, I know that my n and m are up to 1,000. So I'm going to have a dp of size nm at the beginning, and at the end, again, I'm going to have a 4 of size nm to fix that intersection points. And then in OF1, I can check all the cases that how do those two paths pass over this cell and add the corresponding dp's. So this way I can solve this problem easily. Is it completely clear? Does it completely make sense? If it makes sense, please again use the emoji or put a plus in the chat. Okay, nice. Nice. So, this is how this problem can be solved in O of n m. This is nice. So, now let's move on to our last problem that we're going to solve today. This is also a very interesting problem. This one has difficulty 2300, 1198D. So, this problem says that there is a square grid of size n by m. Some cells are colored in black, all other are colored in white. In one operation, you can select some rectangle and color all its cells in white. It costs maximum of h and w to color a rectangle of size h by w. You are to make all cells white for minimum total cost. So you have a grid of size n by m. Each time you can choose a subgrid of size h by w and make them white. Initially some cells are white, some are black. You want to make everything white, every cell white. What is the minimum total cost that you can pay to make everything white? So as I said, each time you can choose an h by w grid, subgrid, and make everything white in that subgrid. And n is up to 50. You have this grid, and as you can see in the input, the black cells are shown with hashtags, the white cells are shown with dots. This is how the input is given to you. So let's get back to the tablets. As I said, each time you can choose an h by w subgrid and make them white. So how can we solve this problem? Do you guys have any idea initially? The cost, as we said, is going to be maximum of h and w. dp of I and j. What does dp of I and j mean? dp of x1, x2, y1, y2. That's great, yes. Yes. I cannot completely understand which language. Is it Spanish that you're using? Minimum cost to pay. Okay. Well, the point is that if you just find the answer, I mean, if you just define dp of I and j and just solve it for a subgrid that goes to I and j, only for these cases we solve the problem. Maybe in future you need to have some more cuts, such that you're gonna need something in here in the middle as well. I mean by cuts I mean that you want to split the grid into several parts and solve them individually, maybe in future. And only just considering I and j might not be enough. On this problem, a better idea, as you guys also mentioned, is to calculate some dp of like I1, J1, I2, and J2, as you guys mentioned. So what does this dp say? As you said, it's gonna say that what is gonna be the answer in the subgrid starting from the cell I1 and J1 and ending at cell I2 and J2. So for any subgrid, we're gonna solve the problem. And this is gonna be n4. I mean, we're gonna have n to the power of 4 states, n to the power of 4 states for our dp. So this is gonna be our dp of I1, J1, I2, and J2. Now the question is that how can we solve this dp? Well, the point is that when you have this grid I1, J1, I2, and J2, well, I know that the number of rows is going to be, let's assume that all the intervals are half intervals. So it means that we have all the rows starting from I1 and to I2 minus 1. So I2 is the first thing that we don't have, the first row that is not inside. And J1 is the first column that is inside, and J2 is the first column that is not inside. I mean, using half intervals always makes your code cleaner. So this way, the number of rows that you have is I2 minus I1. The number of columns that you have is going to be J2 minus J1. Now the point is going to be that initially you have a choice to just make everything white in just one step. What is the cost of that? If you want to make everything white in one step, your cost is going to be maximum of R and C. Let me see what is your question. Who wants to paint all axes inside? Yes, so yes, something, yes, yeah. So we have this case to make everything white in the first place. This way, our answer is going to be maximum of R and C. And let's assume that R is greater than or equal to C. Without loss of generality, we can assume that R is greater than or equal to C. The other case is very similar. So this way our answer is going to be R. Maximum of R and C is going to be R, and the answer is going to be R. So I'm assuming that we have the number of rows is going to be at least as much as the number of columns. So we can either just do it in one step. Yes, it might be a bit ugly to have a 4-dimensional DP, but it's going to be okay. I mean, it might look a bit hard to write 4 dimensions, but it's not. It's going to be okay. So one case is to make everything white in one step, so our cost is going to be R. Also, one case is that we want to, so now we have an answer with R. Now the question is that can we solve it with less than R, with cost less than R? Can we do cost less than R or not? This is the question that we need to answer. Well, the point is that if we want our cost to be less than R, we know that we're going to choose several subgrids, In each of these subgrids, we just sum up maximum of hi and wi. So we have several subgrids. In each of these subgrids, the cost is gonna be maximum of hi and wi, right? The point is that this sum is gonna be greater than or equal to the sum of hi's. When we calculate the sum of maximum of hi's and wi's, this is going to be greater than or equal to the sum of hi's. Well, the point is that in this problem, the point is that if your total cost is less than r, the sum of the heights of your grids that you're choosing is going to be less than r as well. So if in your grid you want your cost to be less than r, the sum of the heights of what you choose is going to be less than r as well. Do you agree with this? Do you not agree with this? So what I'm saying is that if the sum of these costs is going to be less than r, it means that the sum of hi and wi for these are less than r. Therefore, the sum of hi is also less than r. Therefore, the sum of the heights of them is less than r. If the sum of their height is greater than or equal to r, the sum of their cost is also greater than or equal to r as well. So the cost cannot be less than r. So the point is that the sum of the heights is going to be less than r. Do you agree or do you not agree with this? Let me bring this. Do you agree with this? If you agree, please use this emoji or say that in the chat. I just want to make sure that you're completely okay with it. If you do not, or if it is not clear for you, also let me know to explain this again. So the whole point that I'm saying is that if I want my total sum, yeah, sure. The point is that if I want my total cost to be less than r, what is my cost? I mean, when I have this subgrid of size r by c, and I'm gonna choose several of these subgrids and make them whites. What is my cost in each one of them? Well, the cost in each one of them is maximum of hi and wi, isn't it? So my cost is gonna be equal to the sum of, for example, assume that this is h1 by w1, this is h2 by w2, and this is h3 by w3. So the point is that my sum is gonna be sigma of maximum of hi and wi for all these subgrids. And the point is that this cost is gonna be greater than or equal to the sum of heights. So I'm adding the maximum of heights and widths of each one of these tables, each one of these subgrids that we're going to turn them white. So I know that maximum of hi and wi is going to be greater than or equal to max sum of hi's. It's going to be greater than or equal to the sum of the heights. So the point is that my observation is that, my fact is that if the cost is less than r, then the sum of the heights is also less than r. That's all I'm saying. So if the cost is less than r, and do not forget that I'm assuming that r is greater than or equal to c. Since I said that assume that r is greater than or equal to c, so if we choose the whole grid, our cost is going to be maximum of r and c, which is going to be r. Without loss of generality, I assume that r is greater than or equal to c. If c is greater than or equal to r, that's completely the same. I mean, that's going to be only the variables of c and r will change. and I will consider columns instead of the rows. So without loss of generality, since R and C do not differ right now so far, I can assume that R is going to be greater than or equal to C. So if the cost is less than R, then the sum of the heights is also less than R. Because if sum of the heights is greater than or equal to R, then the cost is going to be also greater than or equal to R as well, because it's going to be the sum of maximum of height and width. If the sum of the heights is greater than or equal to R, the sum of maximum of height and width is going to be greater than or equal to R as well. If they are less than R, then the sum of the heights is also less than R. Is it clear now? Please, if it makes sense now, let's use this emoji or say that in the chats. Okay, do you have questions about this part? I mean, this is a very important observation. This is very important to completely understand this. So, I know that the sum of the heights is going to be less than R. What can I say? When I know that the sum of the heights is going to be less than R, there's one important thing that I can say here. So I assume that I know that I have the answer of maximum of R and C. Now I want to make something better than this. I know that, and I assume that maximum of R and C is R. I know that if I want to make something better than this, my cost needs to be less than R, and the sum of the heights must also be less than R. It means that at least one of the rows is not covered by the subgrids that we choose. At least one of the rows is not covered by any of these grids that you choose. If you choose these grids like this, I mean, assume that there are several more lines there. If you choose these grids, none of them intersect with this row, because the sum of their height is less than R. So if you for each one of them see that how many rows they will cover, the sum of these number of rows that they will cover is less than R. Since that we can be sure that at least one row will not be covered by these subgrids. And when we know this, that at least one of the rows will not be covered by any of these grids, any of these subgrids, what I can say is that when this happens, I can solve these two parts independently. So I can just have a 4 on the row that is going to be empty. I know that, I mean, at least one of the rows is not going to have any intersection with any of the subgrids that I'm going to choose. One of the rows is going to have no intersection. I'm going to fix that row and just see that what is the sum of these two DPs and add them up and say that our DP is mean equal to that value. Also, if C was greater than or equal to R, I could do the same thing now for the columns, and I could just sum up these two values. Okay, does it make sense completely? So I proved that if my answer is gonna be less than maximum of R and C, so my answer is either maximum of R and C that we know. So initially I set the DP to maximum of R and C. And now I want to check if I can make better than that or not. I proved that if I'm going to make better than that, there must be at least one row or at least one column that it has no intersection with any of the grids that I chose. That's the most important fact in this problem. If it's going to be solved with less than that, there's going to be at least one row or one column that has no intersection with any of the subgrids that I chose. The point is that I can fix that row or that column and just solve those two parts independently and add up those DPs and see that what is going to be that sum and set my DP mean equal to that value. This way, I said that I have n to the power of 4 DPs and each one of them can be calculated in O of n. So my total time complexity is going to be n to the power of 4 times n. It's going to be n to the 5th. And since n is up to 50, it's gonna be good. And it solves the problem. Does it make sense? Isn't just checking leftmost and rightmost columns already white is enough? Since if it is somewhere middle, it would be really considered a small subgrid as a no, it will not be considered a smaller subgrid. We need to sum up the answer of the left subgrid and the right subgrid. So I mean that, you know, maybe for instance, this is gonna be the case. Assume that you have a 3 by 3 grid, for example, or let's say even you have a 1 by 3 grid. So as I said, and assume that these two are black. As I said initially, I set my DP, I set my answer to maximum of RNC. So initially I set my answer to be 3. Now I know that if I'm gonna solve it with less than 3, there should be at least one row that has no intersection with the subgrids that I choose. The point is that in here, when I consider the case that none of those intersect with the second row, then it's like I want to solve this part independently and this part independently. Oh my god, I forgot it again. Sorry about it. So the point is that as soon as I wanted to solve a 1 by 3 grid. The point is that initially I can set its answer to be 3 because maximum of R and C is 3. At the beginning I set it 3. Now I want to see if I can solve it with less than 3 or not. The point is that if I'm going to solve it with less than 3, there must be at least one row that has no intersection with the subgrids that I chose. And the point is that when I consider the case where this one is not solved, this one has no intersection, I can solve these two parts independently and both give us 1, and I just add them up and it gives us 2. I'm checking one. I'm saying that it's not enough if you only consider the case where you just ignore the first row or the last row. I mean, maybe, if that is your question, that if we can just consider removing the leftmost or the rightmost column or the first or the last row, that is not gonna be enough. Maybe it makes sense to consider that we do not do anything with some row in the middle. Does this answer your question? You would also consider. Well, the point is that, okay, yes, in this case, because there's only one in each side, by removing them, you will consider them. But assume that now we have it like this. For example, it's 1 by 5 and these are black. Then if your cuts are like this, it's not gonna be enough, right? You need to consider that you remove this middle one. So assume that there are so many black cells in here and so many black cells in here. You need to consider the case that you remove this middle row. Does it make sense now? So it's not enough to consider if the first row or the last row do not have any intersection with those subgrids. You need to consider all the rows and see if they have any intersection with your subgrids or not. I mean, you know that if the answer is gonna be less than maximum of R and C, there needs to be some row or some column that has no intersection with any of the subgrids that you choose. There needs to be at least one row or one column for that. So the point is that when we have this, we need to fix that which one is that row or column and just calculate the minimum answer among all these cases. Definitely we will solve more problems in the future topic streams. Today we solved 6 problems. If you also consider that first tape problem, it's going to be 7 problems. But we definitely are going to solve more problems in the future, in the future topic streams. Each topic stream is around 2 hours, and this topic stream is going to now end. But I look forward to seeing you in the next topic streams as well, where we definitely are going to solve so many more problems. I hope that you enjoyed this topic stream and you really learned something. I also want to invite you, now that you watched this topic stream and learned something, I want you to watch something fun as well, and something fun that can be very also inspirational and helpful for you. I have had an interview with Arash, an IOI gold medalist who right now works as a quantitative researcher and earns more than $500,000 per year. And we had a nice interview. He talked about IOI, competitive programming, about his work as a quantitative researcher. You can watch it in here if you want. Now that you watched this topic stream, I want you to watch this. It might be fun for you and interesting. And also you can see all the, if you want to see you can see all the topic streams that we have in this playlist. Nice. So happy if you learned from this topic streams. Sounds depressing, right? No, but it's gonna be inspirational for you if you watch it. You can see that what is gonna be the future of learning competitive programming and getting good at it, and then working in a company. So I invite you. It can boost your motivation as well. So I invite all of you to watch that after this topic stream. Okay guys, again, thank you very much for joining me today in this topic stream. It was nice having you. I mean, you are the only reason that I'm making these topic streams. I really hope that it is nice for you. If you liked the video, I would appreciate it if you can like them here or subscribe to the channel. Also, I would really appreciate it if you share the video with other people who might get benefit from it. I mean, I try to make my videos as good and as helpful as possible, but you can also help it to be as helpful as possible by sharing it with more people. Because if more people watch it, it definitely helps more. So I can do my best. I would also appreciate it if you can help me by sharing these videos with others who you know that this video might help them. And I again want to thank you for joining this topic stream. I would really love to see you in the next topic streams as well. Thank you a lot, guys. See you next time, and wish us luck in the ICPC. We're gonna leave. We're gonna head to Kazakhstan tomorrow to participate in ICPC World Final, and wish us good luck there. Let me see, in 1/5 example, it can be split into 2 subgrids of 1, 3 and 1/2. Yes. But the point is that in that 1/3, it is the last row. So in the 1/5, it is the middle row. So anyway, you have to split it into 2 rows. So if you are going to split it, after a split, it's going to be the last row. I mean, any row is the last row of some prefix. I mean, that's true. But anyway, what I mean is that you need to split it by some point. I mean, you need to do that. Thank you very much, guys. Thank you very much. So see you guys next, and maybe tonight, in our time tonight, our team will gonna have a session. I mean, just some sort of Q&A session with you guys. I, Colin and Sam are gonna be there, and If you want, you can join that as well. I'm not sure if it's gonna be a good time in your time zone or not, but if you want, you can join that as well. Okay guys, see you next time. Goodbye for now. Thank you.